predominantly, but to complete deep learning, to have completeness to deep learning concepts, we are bringing this convolutional neural network. We can apply on even on text data, even CNN. There is two versions to it. Con 2D is for or image or videos, whereas Con 1D can be used for text data problems too. But this is not recommended. There is a dedicated one, RNN. In fact, there are advancements even to RNN. Sorry for that. LSTM, GRU, and then encoder, decoder, and then a concept called attention came into existence, and then self-attention. On top of this, like the transformer in fact uses self-attention transformer. So this is the latest one that we use in right now. So most of the generative AI LLMs are been built on this architecture. And tomorrow we will see these three, and thereafter we will have session on these three, and the remaining options like we will see as part of generative AI. So today we will see this convolution 2D kind of. So how do we solve this image or um, video? I mean, in fact, video is a stream of images, right? It's just we're going to consider everything as image in that case. Basically, when we take an image, or if you look at it, like I know you in mobile phones, you will hear this frequently. 12 megapixel camera. So that is going to give us a 12 megapixel image when we click on, when we use that camera, isn't it? So when we say 2 megapixels, what does that mean? It's going to be 2 megapixels. It's 2 into 1000 into pixels, number of pixels. So around 2000 pixels. And for 12 megapixels is 12,000. Basically, it's like a kind of, let me show you a better view. For example, I have drawn like this line, right?
Small grids like
Yeah, it's going to be like this. If you scroll, zoom out, you can see there is internally, like the way it's going to store this data is basically like in the form of boxes, very small box that you can't even see with naked eye unless you zoom in. So when when we have a high-end megapixel camera, when we zoom in, what happens? When you keep on zooming in, then it's going to be quite blurred. So it's going to be in the form of boxes, right? The reason for that is you're going to see the actual pixels. So that's how you need to look at it. So, but each box is going to be a certain color, a constant color. It can be anything. RGB calculator. Maybe get a better one. You can see that each box is basically, gives us, it's going to have one constant color. I have given 252. Is R stands for red, G stands for green, and B stands for blue. There is other representations to HSV, hue, saturation, value, but this particular course is more on generative AI, so we're not going to focus much on that. So this is when we have intensities, the intensity is ranging from 0 to 255, each value. When everything is 255, that's the max value that we get. This is going to be white color. You can see this white color. Let me change it to, let's take 0. See what we get. You can see that we got some kind of purple. So which is a combination of red and blue. Let me reduce the intensity of blue. So 150. You can see that the kind of pink, right? So it's going to, because of change of these intensities, let me zero down this one. Then everything is going to be blue, but with what intensity? It is 150. So we can have a range of intensities ranging starting from 0 to 255. So totally it is 256. So that is how this data is going to get stored. Internally, everything is going to be numbers. Each pixel is going to have an array of these values. Let's take this color, this particular color is going to be 0, 0, 150. So if we combine all the pixels and it's going to form a image. If you look at this image, So is going to get stored in the form of pixels, isn't it? So each pixel is going to be constant value, even though we can see a lot of colors. But when you keep on zooming in and we're going to look at the pixel level, there's going to be only one constant level. So it's a combination of a certain group of constant colors is going to form a colorful image. But when it comes to real world problems, we are not going to take the color images. So if you look at this image and just imagine, like just consider that our task is to find out the object in this. Whether it is colored image or grayscale image is going to be the same, isn't it? So we usually convert that into grayscale. What is grayscale? It's basically white or black. The intensity is ranging from 0 to 255. Okay. So grayscale scale calculator. Maybe I don't have the right calculator. Okay, I don't have a right proper calculator for this, but the idea is that these colors are ranging from 0 to 255, but when it is 0, it is completely black, pitch black. When it is 255, it's going to be completely white. Suppose let's take that we have intensity 100, it is going to be neither black completely nor white, but it's going to be in between. Then what kind of color it's going to be? Gray, right? Ash kind of color. When you keep on changing this, you can see that you will see some change. So whether is being converted to grayscale or color image is going to be same. But converting grayscale is important. Another reason why we need to convert into grayscale is going to reduce the overload on the system. If the color image or the grayscale the image is going to yield out the same result, then what is the need of having a bunch of arrays? For example, when we have an array like this, 0,255, 150, 150, another array, another pixel. Let's take 150, 22, 25, and so on and so forth. Okay. Instead of this, if we can able to make it like 150, 250, 25, 24. So each pixel is going to be present with only one value instead of an array of values. So when we compare to
Rather
this
than RGB value, like single value, black or white, it will be taken, right?
yeah, so this is going to be taken either black or white. So intensity is ranging from 0 to 255. 0 means black and 255 means white.
White.
Anywhere in between is going to be a combination of white and black. So it's going to usually be various intensities of gray color.
Both the results will be same for finding out the image what it is
The
like that.
same object. So as long as it's same object, if you're trying to find the object, then we're going to it's the same
Same
result.
result. Okay.
Is we can reduce the workload drastically. So in this case, what happens is like each value is going to be considered as an input that will simply explode. It's going to be billions of parameters, which is not possible. Like just for one image, just imagine how the video is going to be. It's going to be 24 frames, right? For every second, you're going to see 24 frames, 24 images. Then it's going to, we need to calculate for the whole duration. It's going to be a humongous amount of data. That is when the CNN is required. Before even we dive deeper into CNN, we need to understand what this computer vision is all about. So character recognition. So let's take finding out a character like A or B or C or number plate. We are trying to find what sort of characters it has. Finding out the exact number, but just by an image. Image classification. Let's take that you have got two images. One is dog image, another one is cat image, right? Cat image, and you need to classify. Let's consider this is an image being provided, and you need to classify it as dog. Or if another image being given, and we need to classify it as cat. This is image classification. Object detection is finding out an object inside the image. So there is this more higher level, and object detection is finding out an object inside that particular image. It's not classifying the whole image. We have a lot of objects here. If you look
Yeah,
at
like
this, we have
finding out
only one
tree
object.
lights or something like that, right?
Yeah, tree traffic lights
Yes.
or humans or vehicles. You can see that, right? So the same. Object detection is basically one level deeper when we compare it with image classification. And what else? Yeah, it's a facial recognition. So finding out the face. Let's take that right now. When we get into organization, there will be a swipe card, wherein you need to swipe, right? So to recognize that it is you, every employee will carry a swipe card, identity card. So just imagine that there is a camera, and based on the face, it is going to detect whether it is you or someone else. Then we don't require the swipe cards, right? That is when this facial recognition comes into picture. Motion analysis is, for security, mostly we use it for security purpose or even for sports. For example, baseball. Uh, so this he's trying to throw a ball, right? I don't know the game, but he's trying to throw the ball.
Yeah,
But
baseball.
which kind of motion will yields out better result? How do we find out that? So we go with this one. So in sports, they use artificial intelligence a lot, and not just this for security reasons too. For example, we want to find out any suspected person in the crowd. So there will be the motion of a person who is criminal in nature is going to be quite different from the others, isn't it? I think a recent case has happened, and not recent case, almost 10 years ago. Um, a suspected motion being observed in Arabian Ocean. A fisherman. Usually, fisherman will follow certain path. Only those paths they will choose. They're not going to go away from the actual path. But they observed something weird. A fisherman or a boat being observed in an unconventional path. Then they even warned, but they didn't respond. Then they fired. Right? That became a very big case later on. So motion analysis can be used even in security and other things. Uh, so image generation in the sense when you give some text, it's going to generate image. So this is again part of generative AI. Let me take a good example, CV tie. So this is one free tool that you can use it for generating images. If you go to create, I think we need to log in here. So you need to give a prompt, all right, so create, uh, generate images. So let's take that uh, cricket batsman hitting six, right? So right click on icon from start generating. Here I'm going to get 4 images. So I required only one, so this will take less time. Just with the text is going to generate image. When you might have heard this word Sora, right? Someone is hitting the ball. Hitting six, but it may not be exactly, but it's giving some output. Which is computer generated image. So we computer vision going to solve these sort of problems. With this, actually, this category of problems will come under computer vision. An example or picture been given. Okay, so that is not the point. Most important here is I think I already explained this in calculator, right? RGB calculator. Same thing with various intensities. Few more examples. Grayscale, I explained why we need it, and yeah, this is the most important one. Why we even need another neural network? Why can't we manage with deep neural network? There are issues with deep neural network. For example, let's take this image. Let's consider that this has been fed as an input, okay, while training. And thereafter, we got the model, and this image has been given as an input to predict whether it is zero or something, O or something. Let's consider it zero. So zero or any other number. Then if there is a slight change, you can see this there's slight change here in the pixels, right? This has been moved up. So there is slight change in it, then it's not going to find out whether it is, no, it's not going to find it out as zero, O or zero, zero. So that is the problem with ANN. So if there is any change in the position, the deep neural, artificial neural network or deep neural network will not, are not efficient enough. Another important reason why we need CNN, convolutional neural network, is it is going to explode with number of, billions of input columns, right? Input features. Then there is no way that, we need very big missions to solve the problem. Then it's humanly not possible, practically not possible to solve image related or video related problems. Right? We can't build models, effective models. That is when this convolutional neural network comes in, wherein it drastically reduces the number of neurons. How does it do? Let me explain this. This is the typical architecture of neural network. Suppose this is an input image. Okay. This is a normal neural network. At the end, it's going to be normal neural network. So input layer, just consider this as the input layer and this hidden layer. We have only one hidden layer. We can have more than one hidden layer, right? The output layer, based on the number of classes, number of categories, we need to mention the number of outputs, in neuron, number of neurons in output layer. Up to here, it is the same. Of course, we will provide image to it. We need additional one. Reason for that is when we take this image and directly if we flatten it out and go with this, come with an input layer. I mean, number of neurons that you're going to have in input layer, it's going to be billions. So we need to do some kind of process so that it can drastically reduce the number of neurons. That is number one. Number two, already explained it. The position can't be solved by deep neural network. This can't, we can, if we feed this image directly to this one, it is not going to solve this problem. It's not going to solve this problem. So the idea is when image being given to some neural network, okay, image being given to neural network, it has to find the object or image overall when it comes to classification, it need to be effective enough irrespective of the position or any slight change to the given input while training the model. Okay, then that's number one. Number two is we need to drastically reduce the number of neurons. Number of neurons in the sense input neurons, input features. What will happen if we don't have, and if we don't reduce the number of neurons? Obviously, it is not possible to solve problems. Like even we can't train it in our missions. We need a military grade, very big missions, right? So we need to reduce the number of neurons. These two reasons is going to be solved by the CNN architecture. How does it solve that? This second point is going to be solved by pooling layer. Okay, it's going to compress. That's all. And the convolution layer is going to extract the important features from this. Each plane, you can see it here, right? Each plane is basically, I think it's better explained with an image so that you can understand it. You can just consider this is the actual input image that I have given at this input layer. So convolution layer, as I told you that there are a number of convolution layers, right? Each convolution layer, each plate or each plane is going to extract some important information from the image. You can see like this. When you provide this input image, just look at these images. These are each convolution layer has produced each set of images. And each image that the convolution layer comes with, it's going to focus on certain area of it. You can see that this is more like, on the window part, right? And this is more going to focus more on the edges part. It's going to focus more. You can observe that this has more better edges than this one. And this has given the overall picture. And the windows been focused a lot compared to this one. So each convolution layer, let's try to extract, important, at least some part of the image. because it's not humanly not possible to extract all the information. Of course, we can take the image as it is. As I told you, that position problem can't be solved. So with these convolutions, we can extract certain set of important features with with each of these convolution layer, a convolution, I mean to say the kernel, and then we're going to compress that data, and then we're going to make it as a normal neural network. We will flatten it. Flatten this is going to have multi-dimensional array, right? This is going to flatten it. That is one-dimensional array. And then thereon it's going to be quite simple. So now the next question is, what is this pooling layer does really? There are two things. Max pooling, I will explain these filters later. So we'll get into the pooling layer first. Yeah, here you have pooling. So basically there are two kinds of poolings. One max pooling, another one is average pooling. Suppose just consider this an image when we have certain number of pixels. What this does is it's going to like, let's take max pooling. If it is 2 by 2 kernel, we call it as kernel filter. Filter or kernel is the same. Just consider that we are applying 2 by 2 kernel. We can even apply 3 by 3. When we mention 3 by 3, it's going to be this part. Okay. 2 by 2 means only this part. So we need to calculate the maximum value in this set of values. So what is the max value in this case? 5232 is 5. So it's going to record 5. The next one is going to move to the next one. It's 4129. Max, what is the max value? It's 9, right? So it's going to capture 9. So we have 5 already. We got 9. And again, it's going to move to the next one. 4112. So what is the max value? 4. And 1300. What is the max value? 3. So it's going to compress in this manner. The average pooling is almost same as this one. Whereas instead of finding out the max value, we are going to take the average. 5 plus 2 plus 3 plus 2. What is 5 plus 2 plus 3 plus 2? 5 plus 2 is 7, 7 plus 3, 10, 10 plus 2, 12, 12 by 4 is 3. We're going to get 3. Same way, 4, 1, 2, 9. It's 4 plus 1, 5, 5 plus 2, 7, 7 plus 9, 16, 16 by 4, it is 4. And so on and so forth. That is how it's going to compress it. So this image is going to convert into these sort of images. Because which is very less, isn't it? Clear?
So after compressing it into four, like after the addition, right? It is storing again in some like matrix form.
Oh, that by itself matrix, isn't it? That box being represent the box is in by
Matrix,
itself
yeah.
matrix, isn't it?
Matrix, yeah.
It's just a tabular form of
And it's still going to compress and store it like that. That's it.
yeah, that is going to compress it so that we can drastically reduce the number of neurons. Can't we apply CNN without a pooling? Yes, we can apply, but the problem is the kind of neurons, the number of neuron input features that it's going to generate, it's going to be billions. You have to have a good system. Even without pooling layer, yes, we can apply it. Will it affect in some way or the other? Yes, of course. But compared to not doing anything, we are doing something, isn't it? That's the whole idea of this pooling layer.
Yeah.
So convolution layer is already you got an idea what the purpose of convolution layer. What I mean internally this is how it's going to look at. This is only neurons, and in fact, if you look at this, these we got as kernels of filters. So these are actually parameters that has to find by the neural network, and these values are not going to be known by us. So initially it may start with zeros or whatever uniform value 1, 1, 1 and all, but it is going to keep on changing it. So it's going to be a set of parameters. Now we'll get into the kernels. Let's take here. Let me take. Okay. So we are going to take kernel or filter. Let's take that. This is the filter or kernel we have taken. 101, 010, 101. So again, don't ask me how we got these values. Basically, initially we start with some values and neural network based on the error, it's going to back propagation. It's going to do back propagation and it's going to adjust the weights. This is actually weights. And we're going to take this one and apply on the image. Just consider that this is a black and white image. It's not even grayscale, black and white. 1001. 1 means completely blank. 0, sorry, 1
Yeah,
means completely
intensity.
white. 0 means completely black. It's not, we have seen color image, we have seen grayscale image. Grayscale is going to have a range of values, 0 to 255. Whereas black and white is completely either black or white kind of. So just for simplicity for calculations, I have taken black and white image. You can see some X image being given, right? Look at this carefully. So we need to take this kernel and apply on this. So we're going to start with this one. So 1, 0, 0. These are the actual values, and the red color values are from kernel. We need to multiply these values. 1 multiplied by 1 is 1 plus 0 multiplied by 0 is 0. 0 multiplied by 1 is 0. 0, 1 here again. 1 plus 1, 2. 0 again here. 0 here. 0 here. 1. 1 plus 1 plus 1, 3. So that is the value you're going to be captured. Okay. The next move, let's imagine that this is, okay, this is how it is. We have taken 3 by 3 filter here. It can be even 2 by 2 or 5 by 5, but it should not go too large or too small. Okay, so 3 by 3 is a better filter. So mostly we use 3 by 3 filter, but it's not restricted to 3 by 3. We can even change that 5 by 5 or 1, 2 by 2, whatever. 1 by 1 doesn't make any sense. So this is, in this case, 3 by 3, right? So it's going to be 3 by 3. You know how to calculate it. So we got this 3, right? The next move is going to be this one. Focus on this. 3 by 3. Select window sliding.
Oh, next column.
Yeah, this part. 3 by 3. The next move is going to be this one.
No, the last will be selected.
Yeah. So as it is 3 by 3 filter, we can't take this one. Next move is not going to be this one because we don't have anything here. The next move is going to be here from this one.
Yeah, downwards. Yeah,
The next move is going to be like this. We call it as striding. Suppose if stride equal to 1, then it's going to move like this. If stride equal to 2, then it's going to be, in the first phase, it's going to be 3 by, just, sorry, I have cough. Please don't mind. So the 3 by 3, and the second stride, as we have second stride 2, it's not going to move here. It's going to move here, 3 by 3. So stride 2 is not recommended. Stride 1 is better. But when the image is very large, we have a lot of data, we go with stride 2 or stride 3, whatever. The next
I mean, can you please explain? Stride one is like from lower to higher to lower, or from right to left? Stride
so
one.
it's actually from left to right.
Stride one.
No, both stride 1 or stride 2 same left to right. It is
Oh,
the way the move next to what will be the next move here. Stride 1 is the next move is going to be this one.
yeah.
Whereas stride 2 after this is going to move to this one, not this one. The move is going to be here.
Yes, yes. But it is 3 by 3, right?
The same 3 by 3. The
Yeah.
next we don't have a next move. At least stride 1 we got 3 moves, right?
Yes, 3 moves. Yes.
Whereas stride 2 we got only 2 moves. Again we need to
Yes.
move here. So that is we may lose a lot of data. That is stride 2 or stride 3. You can imagine what will be stride 3. All right. So that is how we need to apply, and we got this image feature map. But how do we visualize this? Already gave you an example, right? After applying each filter on this image, this is what we got. If you want to see the difference, just focus on this box part. You'll find the difference. What kind of information that it has extracted.
Like something feature selection, like, I mean,
Yeah,
on the back.
some importance will be gathered based on like more. Each kernel will extract some sort of information. Okay. And this part has been completed. I hope we got it. So with another filter, I have taken another filter and applied. This is what we got. Of course, these values again, parameters that neural network has to find out. So initially it's going to assume zeros or some set of values and it's going to find out. We have already seen HE initialization, Xavier initialization, right? So it's not always zero when it comes to when we start with certain parameters. We can even have some variations. Locality is basically the idea behind any image or video processing. Locality is nearby pixels are not drastically changed. That's the whole idea. You can see that there is a drastic change, but if you look at these neighbor pixels, 1111, or the intent, let's take that 150, and the immediate pixel is not going to drastically change, a very slight or meager change. That is what it is all about. If there is a drastic change, then the quality of the models, the quality of the output is going to drastically comes down. So most of the CV models, why we are not getting you know the right quality output is because it depends on this principle that the neighboring pixels are not drastically changed. Drastic in this is extreme change, 0 to 255 kind of. Of course, black and white is totally different. A filter size can be anything. It can be 3 by 3 or 2 by 2 or 5 by 5. But if you go 5 by 5, we are going to lose a lot of data, and 2 by 2 is going to take a lot of time, right? So we need to have that balance. You can see 2 by 2 here. Of course, when it comes to colors, it's going to apply on each color. So whatever you see, let's consider this a color image, and this is going to be a combination of RGB. So basically, this filter has been applied on all the three scales. Each scale, each color will, each channel we call it as, will have its own set of arrays. So what we see as a color image is basically a combination of all these three. Internally, this is how it's going to be. So what is this? Again, this is a kind of three-dimensional array, isn't it? When we have each value with RGB color, right? Let's take that we have another array here. It's going to be multi-dimensional array. So there is a possibility of having more than 3 dimensions. In this case, it's clearly showing that it is a 3-dimensional array. So each plate here is each kernel, and each kernel will produce each set of images. Like in this case, we have 4 images, 4 filters. Each because of this, we are going to extract some sort of importance from the original image, and then we are going to compress it by applying pooling layer. And then once we compress it, we can apply multiple set of convolution pooling layers, not just one set of convolution pooling layer. It can be another convolution pooling layer, another convolution pooling layer, and then we can finally going to come up with the normal neural network. There are a few other topics that we need to discuss, like padding. So if we go with this data, right, with this 2 by 2 or even 3 by 3, what happens is we are going to lose information at the edges. If we take the same thing, so if when we go with this one 3 by 3, let's try 2, then we're going
Change the
to,
color. Select
sorry,
select different colors. Yeah.
yeah. Suppose if we go with this one, or the next stride, just imagine stride 2, we're going to go with this one. Basically, when we go with stride and the kernel 3 by 3, what happens is we're going to lose this information, right? So of course, we're going to consider it as part of 3 by 3, but there's a possibility that we lose this information. So what we does is we add some padding. So we add an extra pixels around it. It can be even large. Just imagine that padding 1. So it's going to fill either with zeros, we call it as zero padding. The advantage is that when we go with this one, just imagine this stride 2, 3 by 3. The next move is going to be this one, right? And the next move is going to be, so we have padding 1. So just imagine there is another pad. Like we can have another convolution layer, isn't it? From here. So the padding is basically you're going to fill with zeros or whatever. Let me show you. Yeah. You can see that we have filled with 0. We can fill with zeros, or it can be neighboring pixels. Suppose 2 is 2, 1 is 1, 2 is 2 here. So we can follow any methodology, but we are going to form this kind of image out of this, because when we apply striding, there's a possibility that we may lose at the edges. By adding this padding, so we're not going to lose much data. So that is the whole idea of this. And here the padding is just one level, right? It can be even another level altogether. So it's better to reduce the stride rather than going bigger values. So, and with padding one, rather than I keep on adding padding, right? If you go with stride, instead of going stride two and adding two pads, you can go with stride one and add only one pad. How do we extract it after applying the kernel? This is how it's going to. So it's going to consider even these two. Earlier it used to stop right here itself. Now we got even this one. So we got these values. Otherwise, without padding, you're not going to get this value. Another example for padding, right? But there are issues with the zero padding, so it's going to be zero down, isn't it? So that is an issue. So we can, there are alternatives for padding. Let me show you how many types of uh, padding in CNN. Many can see valid padding, same padding, the same pixel. Or valid padding can be it's going to be an average of all the pixels around it or whatever. So that's the kind of mechanism will be applied to fill these values. Zero padding means absolute zeros. Pooling layer, I already told you that convolution pooling layer can be a combination, like it's not just one set of it, we can apply multiple sets. And max pooling and average pooling already discussed about it. So why we need it? Just only to compress the size. You can see compared to this one, it got compressed to this one. And another benefit for with the pooling is even though it's going to solve even the position. So with the combination of convolution and pooling layer, we can solve this position. See, it can be this one or this one. It can be completely inverted. It's still going to be considered as this one. But in some cases, it is going to even create confusion. So we need to create proper image. Suppose if you want to categorize 7 with that of L, so we need to have a lot of data. So by default, it may assume 7 as L or L as 7, right? Fully connected layer, yeah. So it's going to be, once we have this multi-dimensional array, we're going to flatten it. Flatten in the sense one-dimensional array. In NumPy, I think I have used Ravel method. The same Ravel method, which is nothing but flattening, we call it as. And thereafter, it's a typical neural network. So you can see that this one being converted to this one. Once we have this fully connected layer, we can have as many hidden layers as possible. And then finally, it's going to be the output layer. Okay. And usually in hidden layers, whether it is CNN or wherever else, we typically use ReLU activation function. And our dropout layer, we discussed it yesterday, I think, with bare example, standing behind the tree, right? So this dropout is going to be quite frequent. We frequently use that in image related problems. And even convolution layer and all, we are going to use ReLU. Now we got into a very important point. So you can see image data augmentation. Image data augmentation is going to address two things. One, what if we have very limited amount of images or videos, very limited amount of data? Then data augmentation is going to be helpful. I'll explain how it's going to be helpful. Another thing is that overfitting. There's a possibility of overfitting. Suppose if I have bear, right, like this, right? I have fitted all sorts of images in this form. What if I got an image like this? Because this is more like, in a kind of sitting position, kind of, right? Whereas this one is standing position. Isn't or let's just say that in this case it has been tilted towards 40, it has been 45 degrees angle, right? So that is something going to be addressed by image data augmentation. So we need to feed data in a way, even if we get some data like this, tilt towards, tilt the image to 45 degrees or 90 degrees or
Oh,
35 tables.
all type of data. I mean, based
Yeah,
on you have to
yeah,
feed that.
exactly. That's the whole idea of image data augmentation. So with that, we can get more images with a limited amount of images, whatever you got from client. Apart from it, it's going to help us in getting a more efficient model. Let me show you. So if you have image like this, it's been tilted to another direction. They're not going to find it out. Just imagine that this is what cat is. Based on this, it is going to consider it as a cat, not dog. But now we'll get into the actual. Just consider this is an image and vertical shift. This is vertical shift, up or down, vertically. You can see the images here, either up or down. Of course, we lose some data. But losing some data also fine because we are giving all sorts of combinations, right? There is a possibility that the input image may not be complete. So even such case is going to be helpful. So if you look at this one horizontal shift, horizontally, either towards right or left. Visual image is this. Okay. Either right or left. You can see the left or right. And there's something called vertical flip. So inverted. So up or down, upside down. Horizontal flip in the sense you're not going to see much difference, but this temple
Mirror
is
images.
yeah, the
Yeah.
vertically been flipped. This part has been, you can see that in this direction. This is earlier this one, and this got into the right part. Rotation is going, we can even rotate it. You can see that if you mention 90, it means 0 to 90. So anywhere in between 0 to 90. I'll explain the code later, but we'll get into the concept first. Shear is basically like, let's take an eraser, okay, and try to compress it. Just imagine that you have an eraser and there is a text on it, and when you compress it, what happens? That image, the text is going to be shared image, right? That's exactly what this does, shear. It's not tilting towards certain angle. It's basically we're trying to compress the image. So it's like some shear force being applied on the image. So when we mention 30, it means 0 to 30. So it's going to generate these sort of images, kind of like a compressed images, kind of. Brightness also, we can change even the brightness. So brighter, too much brightness, you can see here, right? And there is too much darkness. I can see this is much more darker. Because there is a possibility that the input image can be taken during evening hours, right? Channel shift, you can see channel shift is means channel, whenever you hear this channel means red, green, blue in color image. So the channels being shifted in the sense, for example, if the input, let's take 0, 255, 255, if this is the color of a certain pixel, just imagine that it has been no, uh, tilted towards, let's take 250, maybe 50. 0 anywhere 0, we can't make it minus or minus or whatever. So the 255 become what? 205. 205. What happens in that case? The color of the image is slightly going to get changed. Original image is like you have seen it. Now you can see that there is a slight change here. But this is not making it bright or making it dark. The channel itself, the color of the image, intensity itself being changed. In the intensity of the color itself being changed. Okay, so let me get into the actual implementation part. So it's going to be image data generated. That is what we use it. It's going to be same constant thing. Original image. Let's take this is the way that we can load the image. Even the load image comes from Keras, and I already gave the script in this one. So I think I need to execute once and then re-upload that again. So yesterday I told you that I will recheck the script and update it. So I already updated it in Google Classroom. I hope you got that. So we need to convert into NumPy array or a simply array. And then we need to make sure that dimensions into 4 dimensions. So that is the input, that is the kind of input that this image data generator expects. or like, the whole process is going to be. Image data generator comes from again here, Keras processing image. So the only change here is height shift range is going to change from 0 to 2.5. That means 0 to 50%. Even you can see the 50% of the image been lost. Vertical shift, the Y shift range minus 150 to 150. So minus 152, minus 152, horizontal shift, right? It is minus 150 to 150. Same image data center. There is no other change. Horizontal flip equal true, horizontal flip. What rotation, horizontal flip equal to false. Yeah, vertical flip is equal to true. It is what vertical flip. Rotation is 0 to 90 means 0 to 90. It's not exactly 90. Shear means 0 to 30. Okay. So the code part is not difficult at all. The brightness range is 0.2 to 1.5, which means 20% to 150%. Right? So 20% means what? Making it darker. 1.5 means what? Making it brighter. So more than one. More than one means more than the original image. So more than brightness it's going to. It's going to generate a set of images. It's going to be in between 20% to 150%. Channel shift. So it's 0 to 100. So it's not precisely 100. 0 to 100. Okay, got it?
You will change only the augmentation part, right? The rest of the code is same for
The
everything.
rest of the code is same for everything. So the only thing is this one. Of course, we have given only one option here, but we can it's comma separated. We can combine both, like combine various options. That is something
Brightness
we can.
and channel shift, both of them like
Yeah,
that.
it's going to generate a lot of lot of images. So that is something that is you can easily do it, not a difficult thing. So it's not just one parameter. Comma, I can mention brightness range equal to 0.2, 1.5, comma, and all the options if necessary. Do it. It is not. I mean, it's not must, but it's better to do it to get a better model. In some cases, when you get large amount of data, do it in batches. Don't do it all at once. And how do we? Here we have an example for binary image classification. The same, like of course, we have used image data generator here. May not be all the options. I have applied only scaling part here. The intensity is ranging from 0 to 255, right? So if we apply it by 255, what happens? All the values are going to be in between 0 to 1. So that is something rescale not being mentioned over there, but we can apply it. So which is kind of standardized scalar on images. This is how we apply.
So what
Where
is 255?
255 intensity is ranging from 0 to 255, right?
Oh, that one
So
RGB, that one.
yeah, so to bring it down between 0 to 1, we need to divide by 255.
Yeah, yeah, got it.
If it is black and white image, it doesn't make any sense to apply grayscale. So we can completely get rid of it. If the grayscale or color image, apply it to. Here we're going to store all the data in some directory. So that is the reason we need to get this one, and we can't apply, we can't use the normal methods. So flow from directly is going to take the data. And batch size is 32. So what is batch size? Yesterday I explained you, right? It's going to take 32 images at a time. And it's going to make the image to 200 by 200. So if there is a variation in the image size, then it's going to fix to this image. And the binary classification. And we need to apply the typical convolutional neural network. So this part is basically the neural network. We need to flatten it to bring it normal. And the remaining part is going to be as usual. Only part is this part. So wherein we have added convolution 2D and max pooling. And of course, the input image need to be given. And the first hidden layer is going to have 32 neurons and so on and so forth. We have only one combination of max and to say convolution max pooling layer. We can have more than one. Of course, we can mention dropout and various other options that neural network has. We can apply all the methods, absolutely no restriction. Input image shape is 200 by 200 by 300, so which means color image. For grayscale, just 200 by 200. So this one you can ignore. Or else we can mention it as 1. 200 by 200, 200 comma 200 comma 1. Padding is same instance going to give the same pixel values near to it. A ReLU is the activation function, and kernelizer we have used HE uniform. Yesterday we discussed about it, right? So HE, 1 by square root 10, mean is 0. It's going to generate a random value, set of random values with that condition. It's the same thing. Sigmoid, we are using sigmoid because it's a binary class classification. If it is multi-class, you have to use softmax. The remaining process as it is, there is no change at all. Okay. There are autoencoders. I think the autoencoder is being given right here. So the autoencoder is basically the idea is have high number of neurons, compress it, give less number of neurons, and then again extract high number of neurons. So this is what we call it as autoencoder. The advantage is that we can solve overfitting problem or vanishing gradient problems. Overfitting problem in sense, suppose if the position of the image object is being changed from change, right? We have seen L7, right? The same thing. We can solve effectively with autoencoding. And it's going to solve vanishing gradient problem also. Vanishing gradient problem in sense, when we keep on multiplying these differentiations, what will happen? It's going to almost near to 0. So that is something can be solved with autoencoder. Prevents overfitting. That's the reason why we obviously it's basically trial and error. So usually what happens is like they may not even know what will happen. So they keep on trying it and they get the results. They keep on checking. So based on this, it's not the other way around. It is not that they want to solve the overfitting problem and they came up with this. They keep on trying it and it got solved this one. So that is how they got it. Okay. Nothing is magic. So they do a lot of experiments. Prevent overfitting and all, like we have seen it, and it's going to solve this vanishing gradient problem. And we can even have multiple stacks. It's not just one combination of it, multiple stacks like this. When you keep on decreasing and then keep on increasing, we can have more than that. Let's take 128, 64, 32 neurons, 64 neurons, 128 again. Or else 256, 128, 64, 32, we can stack it. Vanished gradient problem, yesterday I explained it clearly. When we differentiate it, the denominator is going to become square in the case of sigmoid, right? Okay, there are variations to it. Yes, so, okay, it's already 9:55. I'll explain it tomorrow. Basically, what happened is like CNN is the base architecture, and they started a competition called ILS-VRC. ILS-VRC. So it's ImageNet Large Scale Visual Recognition Challenge. It's a competition wherein they provide bunch of images like this ImageNet, thousands of images, millions of images. So they give this image set of images. I think around 60,000, 70,000 images. So they give these images and they ask you to classify it. So based on top of CNN, they keep on modifying the architecture, right? They came up and obviously they come up with a better one. So whichever gives better accuracy, obviously that particular neural network is going to be better. We don't know which combination will work, so we need to keep on trying it. This competition comes up with a lot of architectures like this. You can see that LeanIt, LeanIt, LXNet, VGGNet. There are many, in fact. Okay, so we will see that tomorrow. Any questions in today's session?
No, sir.
All right. We'll meet tomorrow. We'll conclude
Okay.
CNN. If possible, we'll start RNN or else next week.
Oh, thank you, sir.
Thanks for joining.